All right, welcome to everyone to the Master Naturalist program. This section is on streams, how they function, and how to manage them better. I'm Rebecca Schneider. I am a faculty member in the Department of Natural Resources. I do research, teaching, and extension all around the issue of sustainable, ecologically based water resource management. Christy's asked me to provide this overview, and I've loved doing it every year, and usually we do it in person, so I'm sorry I won't get to meet you in person this year. You're getting a condensed version of part of a class I teach. It's a lot of information. Normally this would span several days. It'll be about an hour and a half total, and I realize it's a lot of content to process. However, I hope I'm trying to give you the foundation of the information you need so that you could almost do anything you want in streams and actually solving problems with streams and managing streams. And basically, the first whole part is all about the natural processes of how streams function and their ecology. And then the last part is about how to manage those streams, and it builds off of what you'll learn in the first part. I've divided into part 1, part 2, part 3, and then section 2. And in part 1, we're going to start with watersheds, the basic framing of where streams occur and how they function hydrologically. Then we're going to look at groundwater and geomorphology, and all these come together to drive the ecology. And then I'll mention something called ecosystem services that we benefit from having nice, healthy streams. Let's get started. So what is a watershed? A watershed I view as like the bowl. It's the bowl that all the rainfall falls in, and it runs down through the bowl and creates the stream channel network. The definition is the total area above a specific point on a stream or river from which water drains towards the stream. So I think of it as a bowl, and the lip of the bowl is the top of the hills. And why this watersheds are so important is watersheds determine how much water you have to work with in the bowl, in the landscape. It's all the water, you only get as much as falls into your bowl. And on the other side of the hills, that's another bowl. You don't have that water to work with. There are different terms that have been used for the watershed, and they're kind of used interchangeably. Catchment, river basin, subcatchment. There was an attempt made by Dr. Tom Schuler to actually organize the terminology relative to the size of the bowl, and he used catchments to be less than about 0.5 square miles. A watershed was 10 to 100 square miles, and basins were 1,000 to 10,000. And you will hear people talk about river basins, but in generally, I have found that people use them almost interchangeably. River basins are really important because they really determine how much water you have to drink, to irrigate crops, to do anything with. And they're even more important almost than the political boundaries. Knowing who lives in your bowl is determining how much water you have. So they're very important to know who lives in your bowl. And basically the world comes down to 10 or 12 main rivers with everybody living in one of those river basins. For example, most of Europe falls into the Danube Basin. The Amazon River encompasses about 8 different countries. So understanding watersheds is really important. And then within each large river basin, there are smaller and smaller sized basins that all feed in. And that's what Tom Schuler called the catchments. So how do you know where the border of your watershed is? Where's the watershed divide? In the United States, EPA has put together a website called Surf Your Watershed. This is not in your packet. I just put this in today. And so it actually identifies watersheds all across the country of different sizes. They have a whole numbering system for small to large watersheds and gives you lots of information about your watershed. But I think it's really worth knowing how that watershed divide is figured out. And then that way you can figure out for yourself. And the way we do it is to use a topographic map. And you find where the top of the hills are, find where the lip of the bowl is, where are those hills that surround the creek or the river. And the way we do that, and what's really great, is that the U.S. Geological Survey, back in the 1950s, mapped the entire United States, continental United States, at a very fine resolution. They divided it into these topographic quadrats, 1 to 25,000 scale, so you can actually see buildings. And then every one of the quadrats has on each side of it the name of the next quadrats on each compass point. So this is what you're looking at is the quadrant for Alpine, New York, which is where we used to have hold the Master Naturalist workshops. And the red circles show you the scales on the side, each side of the map. There's a compass direction. And this is a topographic map. So what you're looking at is brown lines against a matrix of green or white. And green in this case is forests. So if you've never looked at a topographic map before, when you take something like a hill, they want to show it in a flat two-dimensional format. And so what they do is for each increase in elevation of about 10 feet, they draw a contour line. And when you're looking at that from above, it looks like a series of concentric circles. That's what a hill looks like. And so the very top of the hill looks like a little small circle. And what we want to do then to find the watershed divide is look for all the little circles and then connect them up and draw a line from one to the other to say, there's the watershed divide around our stream. I thought I'd give you an example where you could figure out where the watershed divide is for this small creek called Banfield Creek. This is a subset of one of those topographic maps. And where the red arrow is pointing is actually the camp at the Arnott Forest, and those little black dots are actually the buildings. And let's say you wanted to know where the water was coming that we were drinking if we were going to drink it out of that stream. Or suppose you bought a house next to a stream and you were going to drink the water. You'd want to know where was that water coming from and what was happening in the watershed. Was there anything that might contaminate your water? Maybe it could be a giant parking lot with runoff from the parking lot. It could be cows. It could be any kind of thing. So where is the watershed divide? What you want to do is take a minute and draw in the watershed divide on the map. And that should be in your packet that Christy sent you. And so you want to know where is the divide around all of Banfield Creek, and you're going to connect the dots. You're going to find those little circles that represent the top of the hills and draw a line between each dot. And you should end up with like a big oval that goes around Banfield Creek. Now, a good indicator is that if there's a creek like the one in the lower left of this map that's flowing, that's not part of your creek, there must be a hilltop right between those. So take a minute and draw in the watershed divide. Okay, I hope that made a lot of sense to you. This black line represents where the watershed divide is for Banfield Creek, and I've put red arrows to show where some of the circles are that you would have included as you drew in your divide. And now you know how to figure out the watershed basin. Again, some of this has already been done for you in Surf Your Watershed. There are now computer programs, very good ones that will work with digital elevation maps based on satellite measurements of topography, and they figure out the watershed divide. So there's lots of electronic ways and digital ways to do this kind of mapping for whatever purpose. But to me, it's always nice to know how to do it yourself. All right, once you know where the watershed divide is and how big your bowl is, you know a lot about what's going on with your stream and water in your watershed. First of all, you know, you can calculate the total amount of water. I mean, you only get as much water as falls into your basin. That's all you have to work with. But you also know something about the quality of the water. When it rains or snows, that's pretty close to pure H2O, like a bottle of distilled water. But as soon as it hits the surface and starts moving through the watershed, it begins to pick up substances. And then you know something about the water quality. When the precipitation hits the surface, it basically follows one of two pathways in the eastern United States. If the surface is relatively impermeable, worst case scenario like a parking lot, it runs off the surface, but it could just be soil that's not real permeable, and it's a hill slope, and so that water runs fairly rapidly downhill into the creeks, into lakes, and eventually down to the ocean. That part is called runoff. If it is very porous soil, lots of holes in it, lots of roots, organic matter, the water will infiltrate into the soil, percolate down until it hits a solid substrate like a bedrock, and begin to fill up all the pores, and that's called groundwater. It doesn't just sit there. Groundwater also moves sideways or laterally downslope and ends up in our streams, our lakes, and eventually into the ocean. And given that you only have a certain amount of water that comes into the watershed, there's a balance between how much runoff and how much infiltration to groundwater can happen. The last part of the hydrologic cycle is evaporation and transpiration, called ET. Out west in the Great Plains and where it's drier, ET takes a big role in what happens to the water in the watershed. But in the northeastern United States, it's pretty much either runoff or groundwater. All right, so when we talk about the stream channel network, streams, we're talking about the runoff component. Oh, that's what we usually think about. So runoff moves through a stream channel network. I love this photo here on the right by Arthur Bertram, because it shows kind of like there's the hill, the top of the hill, which is the watershed divide, excuse me, and then the stream channel neck that's forming as it moves through the landscape. There have been different classification systems that have been created to kind of tell you where you are in the stream channel network. The one that is the most typically used is called the Strehler ordering system. And what that does is say the first time a stream shows up on a map when it's very small, that's a first order stream. When two first order streams come together, they create a second order stream. And two second orders create a third order, and so on. The first and second orders are typically called your headwater streams, and you've probably heard that term. That means the small streams at the top of the watershed. What's interesting is that if we were to measure the length, and I'm pointing to these now, of all the first orders, add those up, and then all the second orders and add all those up, it turns out that that represents almost 3/4 of the total length of the stream channel network. So most of every watershed is really these small headwater streams. This is important because they're very different in how they function. The headwater streams are very narrow, and therefore the canopies of the trees overhang those streams. They have lots of leaves falling into the streams, they're darker. And so there's not a lot of light that gets into headwater streams during the growing season. Instead, and therefore like algae can't grow and plants don't tend to grow too well without the light. And so the food that fuels the organisms that live in the stream is based on the litter falling from the leaves. As you move downstream and the streams come together, first coalescing to seconds and seconds to third, finally you get big enough that light can hit the stream bed. Now algae can grow and plants can grow, and that is the basis for the food web. So it's a big difference as you move down through the stream channel network. All right, when you're looking at a stream, the key process is to understand is that there are natural patterns to stream flow. That is, there are times when the water's high and times when it is low. We use hydrographs to document these patterns. This is the hydrograph, 1 week of data. On the bottom axis, going across horizontally, is the date. And so there's October 12th, October 13th. And on the vertical axis is the depth of water in the stream. This is a hydrograph for a 1 week period during a rainfall event. And what you see is that the water was low, around 0.5 feet in depth. Then it rains. Not surprisingly, the stream got deeper. And then it stops raining. It continues to be high for a while, and then it gradually drops back down and approaches again. It's still higher than the 0.5 feet depth it originally was at. The peak that occurs during the rain is the surface runoff peak. And that's what we're mainly focused on right now. But notice that way after it stops raining, there's still water in the stream. And that's coming from groundwater. It's called base flow. We'll get back to that. So how do we get these data? How do we know how do we create a hydrograph? So for thousands of years, it was just done using some kind of a staff gauge with recordings made. So the longest databases in the world on water depth are done in the Nile River using a Nilometer, where they recorded the depths on the steps adjacent to the Nile, and they're thousands of years long. It's incredible data sets. More recently, we use staff gauges like in the lower right, that just is like a ruler that's permanently fixed, and you record the data on it. Obviously, in the past 80 years, we've done advanced considerably. So now the U.S. Geological Survey, who is responsible for monitoring flow in our rivers, uses automated systems like in the upper right corner, in which there is a buoy, a little float that floats up and down as the water levels rise and fall. and it records actually digitally on a recording device what the water depths are. And these are actually delivered in real time in places right to the internet. So you can actually see real time data. In some places they install a weir where they can control the flow so they actually know exactly how much water is going in through the stream while they're monitoring it. This is the key part about that. Once you have a hydrograph, you begin to look at what the long-term patterns of water are in the stream. And what we have figured out is that there are natural hydrologic regimes for every river in the world. The natural hydrologic regime is the annual pattern in the timing of water level fluctuations relative to some point on the shoreline. And in this photo, you can see on the left side, the photo shows the water relatively shallow during the summer, and at the exact same location, during snowmelt in the spring, that site gets flooded. The predictability of these natural rises and falls is the key point. They're now called environmental flows, the natural hydrologic regime, and there are 5 key characteristics: timing, frequency, duration, magnitude, and rate of change. So timing, when does flooding occur? Does it occur in the middle of the summer when everything's growing? Does it occur in the middle of the winter when everything's dormant? How often does it happen? Is it every year or is it once every 50 years? How long does it last? Does it last a day or two, or is it lasting for months? And think about this, if you have houseplants at home, you could put them in your bathtub and flood the bathtub. Some of them would survive after 3 days, but some would not. They could not handle that long of being totally flooded. How big? Magnitude is the next parameter. How big is the flood? If you're a tree, it makes a big difference if just your roots get flooded, as opposed to if all your leaves are flooded and no light can reach them. And then rate of change. How quickly does the flood event come? Does it happen over days or weeks? And if you think about many things like a turtle, if it's a slow rise in water level, they have a chance to leave and not get flooded or washed away. But if it happens very rapidly within a couple hours, then they don't have much time to adapt. Fish, plants, and other organisms are adapted to and dependent upon the natural flow regime. So let's look at the natural flow regime for 6 Mile Creek. This is the watershed and the river that feeds the reservoir, which is the water supply for the town of Ithaca, New York. And that's the topographic quad. And we've outlined the stream 6 Mile Creek for you and put in the red line to show the watershed divide. The U.S. Geological Survey, again, my heroes, maintain about 10,000 different gauges, water level gauges around the entire United States, and report the data on this website. And you can go to this map, or you can put in an address, and you can search and find the nearest USGS gauge, and it'll show you the data. You put in what parameters you're interested in. And so you can actually see for many of the sites, that's real-time data. You can look at the water depth right now for Ithaca. There's actually 2 separate gauges on 6 Mile Creek, and we could look at the water level right now. So this website is really powerful. This is the hydrograph for 6 Mile Creek across the growing season of 2014. On the bottom, it's now the time period is from May 17th to September 6, 2014. And a hydrograph can be any length of time. It can even be just 24 hours if you're looking at a storm come through. And on the vertical axis is gauge height in feet. And what you see is that most of the time, water level runs around 0. And you see a negative value because they had to shift the gauge when a lot of erosion occurred. So it's not really the baseline's now running at around minus 0.2 feet. But the deepest the water got during this 1 year was 3 feet. So what's the natural hydrologic regime? The way we calculate this is we look at many years of data. We take the average, what the water level is in each month throughout that year over a long time period, and we plot it. And this is the average set of mean monthly flows over about a 10-year period for 6 Mile Creek. And what you see is a peak in March and a low level in September. Now note, New York State, where Ithaca is located, gets about 3 inches of rainfall every month. So in theory, the creek would have the same amount of water running through it all the time, but it doesn't. On average, we get a peak in March and a low point in September. So think a minute, what's driving that? Why do we see this change in water flow over the course of the year? Well, hopefully, if you're from up here, snow melts in March. And so all that snow that built up over the winter melts in a short amount of time, and that causes a peak every year in March. In the summer, evaporation occurs as the temperature is warm, and plants transpire a lot of water in the landscape. They're sucking water out of the landscape, capturing it, moving it into the atmosphere, and so we have a low period in flow during September, August, September. This is the pattern, basically, the natural hydrologic regime for all rivers in the northern United States because the same processes are acting. So knowing the water depth is really useful. It tells us a lot about what organisms are experiencing, and it's useful to us if we're thinking about building a house right next to the creek if you want to know whether it's going to flood or not. But it would be really useful also to know something about the quality of the water that's moving through the creek. So, for example, here's a news article about a truck that broke through the bridge, fell into the creek about a decade ago. And they were very concerned because it spilled at least 100 gallons of gasoline into the creek. Now, if the creek was really flooded, super flooded, and sometimes it gets almost up to that bridge, the bottom of the bridge, then 100 gallons would be quickly diluted, almost to the point of non-detectability. But in this case, if the creek's very low, when 100 gallons comes in, it's highly concentrated to toxic levels. And remember, this flows down to the drinking water reservoir for the city. So knowing the total amount of water flowing in the stream is a really useful thing. What we're talking about is called discharge. That's the volume of water that flows through the stream per unit of time. It's typically reported as cubic feet per second, cubic meters per second, gallons per second sometimes. It's a volume in a unit of time, and it's designated with the letter Q. The way it's determined is to measure the velocity of the water times the cross-sectional area of how much water is flowing. Now, think of this, explain this better. Think of this in terms of a faucet. You have water coming through out of the faucet, and you're capturing it in a measuring cup. That's the left figure. If I want it to fill up faster, I can do two things. I can turn the faucet to a higher rate and have it come in faster. That's the velocity. Or if I had a wider pipe, wider diameter to the pipe, more water would come through at the same velocity. So what I need to know is the cross-sectional area of that pipe times the velocity, and that gives me the flow in gallons per second or cubic feet per second. In a stream, we do the same thing effectively. We want to know the velocity, so we use a flow meter, and basically you could throw like a lemon in the creek and measure how long it takes to go a certain distance. But we use something, a piece of equipment to give us a more precise measurement. And then we need the cross-sectional area. So we measure the width of the stream and the depth, and if you multiply those two together, you get an estimate of the cross-sectional area. When we need a more precise measurement, as when U.S. Geological Survey takes the data, they will divide the stream into little segments and then take the width and depth of each of those little segments and then add all those areas together to give a more precise measurement. Our staff gauge, or our continuously recording water level monitor, only tells us depth, but we really want to know discharge. So we have to know the relationship between how deep the water is and how much water is flowing. This relationship is called a rating curve. In front of you on this yellow-green graph is a rating curve for that 6 Mile Creek site. On the bottom, on the horizontal axis, is discharge in cubic feet per second in logarithmic scale, 1, 10, 100 cubic feet per second. And on the vertical axis is the gauge height in feet. And what you see is that we now have a relationship. We don't have to go out every day to measure discharge. We just need to know what the gauge tells us in terms of the depth. If it says it's 3 feet deep, we're getting about 100 cubic feet per second. You'll notice most of the data points fall in the middle towards the 10 to 100 cubic feet per second. What that means is that big giant storms occur relatively infrequently when water depth gets actually up above 5 to 7 feet in depth. And so we don't have a whole lot of data. And actually, most people, we really shouldn't be having people going out when these are torrentially flowing, unless they can take data from a bridge. They shouldn't be in the creek trying to collect data. So we don't have a lot of data at the really high levels, nor at the really low levels. So now we can superimpose. At the top is the hydrograph showing the gauge height at the 6 Mile Creek site. This is just from September 2nd through September 18th in 2019. And on the bottom graph, it's the discharge, the comparable discharge. So as we saw the rain event and water depths increased from 0.65 feet to 1 feet in depth, that corresponded to an increase in discharge from about 12 cubic feet per second to 45 cubic feet per second. Really useful. So this is the discharge hydrograph for the entire extent of data for the 6 Mile Creek when they started measuring in 1997 through 2019. You're seeing the rise and falls in the water level. And zooming in a little closer, you can see that the rises tend to occur in March, around March, and then in August, again, it's low, but there's a lot of variability from year to year. So I showed you those hydrographs from 6 Mile Creek, and that told us a lot about the timing, the frequency that occurs every year when snowmelt occurs, the magnitude, a couple hundred cubic feet per second to 1,000. I want you to see, this is not the same. Every river, apparently there are about 15 typical patterns of what the hydrographs are, or the natural hydrologic regime is around the world. In the southeastern United States, for the rivers that flow along the Atlantic coast, these are 2 typical hydrographs. The bottom one shows the Savannah River in Clio, Georgia, and again, we see that peak in March. But look at the top hydrograph from the Apalachicola River. Again, there's a rise in the middle of the winter, but the magnitude is amazing. Every single year, the water rises from 30 feet in elevation, in depth to 50 feet. That's a 20-foot rise in the water depth every spring, every winter to spring. That's the magnitude of change. It's way, way more water moving through these giant rivers than what we're seeing in Little 6 Mile Creek. So here's an example of a real hydrograph for a small pond that's part of a kind of stream system out on Long Island. And I wanted you to see this unusual hydrograph and figure out what it is. What's the natural hydrologic regime experience? In this case, I'm interested in the plants that occur right at the edge of this pond, which is right now dry, as you can see, and where the red arrow is pointing. What do those plants experience as a flooding regime? And the graph above is the plot of the water level in that system from 1976 through 2019. On the vertical axis is the water depth and elevation of the pond above the pond bottom. And the red line that's going to cross is the elevation right where the shrubs stop occurring, okay, the edge of the shrubs. So take a minute and look at this. And what you see is that above, many times the water level is above the red line, which means the shrubs are inundated with water. And many times that blue dotted line, which is the depth of water, is below the red line, which means the shrubs are now dry. When you look at the frequency and look closely, what you realize is the natural hydrologic regime for this site is that it floods for 2 to 3 years at that point, and then is dry for 2 to 3 years. Then it floods for maybe 1 year, and then it's dry for a year, and then 2 to 3 years, and maybe sometimes 4 years, and then it dries for 2 years. This is the natural hydrologic regime. It's really critical. The reason is these shrubs would actually take over that entire very flat pond. The pond is really shallow, but the seedlings of the shrubs cannot handle being flooded when they're really young. So if it stays flooded for 2 to 3 years, they die off. In this case, this pond is managed by the Nature Conservancy. These ponds, of which there are about maybe 30 total, all occur in the northeastern United States. They have the highest concentrations of rare plants in the entire northeastern United States. And the plants are those ones growing out in the flat bottom of the pond. will not be able to survive if those shrubs take over. And so that natural hydrologic regime that consists of 2 to 3 years of flooding and 2 to 3 years of drawdown is what maintains the plants in this pond. And a note, well, I call it a kind of pond stream because when it's very high water levels, the water flows from one pond to the next very slowly. Effectively, it's like a little stream system, but they call them ponds. Okay. That's the end of the first section, which was really giving you all you need to know about the hydrology of streams. Now, we're going to talk about the other pieces that contribute to the ecology. First, we'll start with groundwater. If you recall, when I first showed you the hydrograph, I showed you the runoff piece, which was the amount of water that came into the streams right when it was raining and immediately thereafter that raised the water level in the stream. And then I said, but you know, sometimes days and weeks later, after it stopped raining, there's still water in the stream. Where is it coming from? That's the water that's coming in, it's groundwater from the surrounding watershed, and it's called base flow in streams. And I showed you this cross section of a watershed, and to remind you, water infiltrates the soil, it percolates down until it hits an impervious surface like bedrock, it fills up all the pores, and that moves laterally and down into streams, lakes, and into the ocean. This is what that looks like up close. You see the unsaturated zone, which has just the water infiltrating through it, and then the saturated zone where all the pores are filled with water, deeper down in the soil, that is the groundwater. And in the cross section below, what you see is groundwater that moves subsurface laterally and ends up in a stream. And where water enters the watershed, that's called the recharge area, where water's infiltrating down to fill the groundwater aquifer. So as groundwater moves from a recharge area, it moves subsurface, it picks up dissolved nutrients and gases, it's actually habitat for organisms, and then it discharges into the shoreline of a stream or lake. That's where the groundwater comes back out. For streams, that flowing groundwater is very important to them. So here's groundwater coming into the shoreline of a stream. How much of the flow that's in the stream is due to groundwater? And that's a really important question. So there are various methods for figuring that out. One that's very often used is to take the hydrograph and quantitatively separate out the part that is due to runoff, and that's what these different lines are in this hydrograph, and there's conversations about which line you use. And all the water above the line is due to the runoff, and all the water below the line is due to groundwater, and you add up the volumes of water for each unit of time. So Professor Dr. Tom Winter, researcher with the U.S. Geological Survey and a group of colleagues, set out to figure out how much groundwater contributes to streams. And they went to all these different sites around the United States, analyzed the hydrographs, and each of those circles shows us one station, and the blue part is what the groundwater contribution to the total stream flow is. And you can see it ranges from 25% groundwater contribution to about 5%, some cases 80%. And what they found is that on average, 54% of the flow in our streams is groundwater. Not runoff, it's groundwater. And so if you don't want your stream to run dry or to be polluted, you really have to focus on managing groundwater in the landscape. There's a term you'll hear a lot, and I just thought I would mention it so you know what it is. It's called hyporheic zone or hyporheic flow. And what that is, it's the groundwater just as it enters the stream. There's a zone about 10 meters on each side of the stream, about 1.5 meters below the stream, where stream water and groundwater mix. Subsurface is not up in the stream, it's literally in the soil. That's called the hyporheic zone. It's very important to the chemistry, the chemical changes that happen to organisms that live there. And so that's just a term you might hear. All right, now geomorphology. And in a minute, you'll see why all this comes together. The velocity and the discharge, that's the amount of water flowing in the stream, drive the shape of the stream at multiple spatial scales, okay? And so in this schematic, you see a very curving, sinuous, meandering stream. There are little pieces of the stream that have broken off called oxbows. There are point bars where sediment builds up, deposits of material occur. This is all the geomorphology of the stream. This is an aerial photo showing a similar system for the Moose River and the Adirondacks. It's one of the most meandering streams that I've seen. So certain things are happening when that water is flowing in the stream. It's not all moving at the same velocity. If we were doing our discharge measurements, we would see there's one part of the stream where it moves slowly, and there's usually one section where it moves the fastest. That section of the stream is called the thaw wag, okay? It's the flow path of highest velocity. It has a ton of energy. It kind of moves from side to side of the stream, or oscillates as it moves downstream. And as it moves then, that high energy part is the part that scours out the bank. It carries a lot of material with it. And then on the slower parts of the stream, that's where that material then settles out. And you get deposits called point bars or some kind of alluvial deposits. What this translates to are parts of the stream that are shallow, they have high flow. Those are called the riffle areas. They tend to have like coarser rocks and boulders because the finer stuff washes away. They tend to be very oxygenated because the water is all whipped up and bubbly where it goes through the rocks. And then you have pool areas, which are slower, deeper, quieter areas. So this is a cross section of what that looks like in the stream with a riffle and then a pool and then a riffle and a pool. The velocities are higher in the riffles and there's more oxygen. Okay, how does all that come together to affect the ecology of streams? The flooding is first the driver, the main driver. It's called a master variable. It surrounds the roots, the stems, and leaves for varying amounts of time. We just looked at the natural hydrologic regime. This photo is a giant willow tree right next to a stream, and all those red things in the water are its roots. It has tons of roots. It's almost like hydroponics. It's just growing and sucking nutrients out of the stream as it goes by. The flooding can have high energy, can be very scouring, and so that's why it's also a variable. It can lower light levels, and it affects the amount of oxygen that's available in the soil for plants. So flooding is the master variable. Most people cannot even be underwater for more than a minute holding their breath. You need to breathe. So low oxygen controls almost everything. I mean, a high versus low oxygen, how much is there is really critical. So plants have to be adapted to this flooding, in particular to the oxygen levels and how they're changing. One way is they do it morphologically. So they can have shallow roots near the surface where they're more likely to get oxygen. They can have holes in their bark called lenticels. They have ways to deal with a high energy of flowing water with buttressing their trunks. And in tidal systems, they actually have all these adventitious roots like mangroves. So these are different structures that they have as adaptations to high energy, waves, flowing water, and to get oxygen. They also have physiological mechanisms, and we won't get into all those chemical ways they deal with anoxia and low oxygen, but they have adaptations that way. They have strategies they've evolved to deal with regeneration. So for example, many have long-lived seed banks. They release their seeds and they sit in the soils and wait until the soil gets oxygenated for them to germinate. And they have incredible capacity, many plants do, that grow in wetlands, to wait hundreds of years, sometimes thousands of years, and they will germinate when they're again exposed to oxygen. They have seeds that are dispersed by water because they're grown right by flowing water, so they have to be adapted to float. And they also have the ability to reproduce vegetatively from tiny fragments, little pieces of branches. So willows in particular, you can break off a branch and it can reproduce from that. And it's a strategy for restoring streams to use lots of segments of branches of willow and bury them in the shoreline of the stream so they will grow and root. This is a graph just showing you how different all the species are in their ability to tolerate flooding. Each dot indicates the limit beyond which a species cannot survive inundation. So in terms of percent of the inundation during the growing season. So for example, tulip poplar, a beautiful, tall, majestic tree, can only stand inundation for 10% of the growing season. Sycamore trees can last 25%. If they're flooded for 25%, their roots are inundated, they will still survive. There are species like bald cypress and water tupelo. That's a photo of the water tupelo in the top right. They can actually handle, once they're established, germinate, they can handle being flooded 100% of the growing season for years and years. It's just during the seed germination phase that they need to have a drawdown. So there's a great database about how tolerant plants are to being flooded. It was developed during the 70s and 80s when we began to recognize all the ecosystem services of healthy wetland and streamside habitats. And I'm going to talk about those benefits in a few minutes. But they developed a database for every single plant that occurs in a wetland and whether it is obligative upland, that means it can handle flooding, obligative wetland, which means it has to stay flooded all the time, a facultative wetland, which can handle some flooding, some dry, doesn't matter too much, and facultative upland, which tends to prefer drier conditions but can handle some flooding. That is the U.S. Fish and Wildlife EPA wetland plant list, and right now I found it on the at the www Army Corps of Engineers Army military site. So the database is out there in a variety of formats, but basically it's a list of thousands of plant species by region and whether it's one of these categories. This is what it looks like from the 1996 summary. And that's just the A's for allness and red maple, acers by region and whether or not they're facultative, upland, facultative, wetland, obligative, or whatever. And so you can actually learn a lot about what plant species can deal, and it's useful. You can use this to help do restorations. You can use it for a rain garden design. It's a really powerful database. The second big kind of theory that drives our understanding of streams and rivers is called the river continuum theory. And as we noted when we talked about the Strahler stream water, streams increase in size as they go further downstream. And the order in this graph plot on the right, the schematic shows stream water 1, 2, 3, 4. The width in feet starts at 1 to 2 feet. A third order is about 12 to 25 feet wide. By the time you get to a seventh order, it's 160 feet wide, and so on. So we go from being a headwater stream that is narrow, shaded with an overhanging canopy. It is fueled by inputs of leaf litter, and that process is called allochthonous. And then as we get further down, the river becomes wide, deep, receives lots of sunlight, and is fueled by phytoplankton, algae, and plants. What's interesting then is that the entire food webs are change as you move down the stream channel network, the river system. In the headwaters, different invertebrates occur, the bugs that live in the stream basically. And the majority, 75%, shown by the circle at the top of the page on the right, are shredders. They shred and chew up the leaves. And then the finer particles float downstream, the parts they didn't get to eat. And collectors, which are in the next one, are the white squares, become more and more dominant. There are predators in each category. These are all the invertebrates that eat these bugs, other bugs that eat them. And then as you get down to the larger order streams, we have more and more grazers and predators that now work down there, and collectors, okay? I am not a stream invertebrate scientist, but they're very cool. I think if I had a whole nother lifetime, I'd get really into learning about them. These are the shredders, and so many crustaceans, stoneflies, and these are caddisflies. They form little cases of stones around the larva of the insects. So these are the immature form of the insects. And these guys chew up, the shredders are the ones that chew up the leaves. This is an example of a grazer. So the grazers actually scrape algae from the rocks. So when you get further down into the river system where the light can penetrate into the water, you get algae to start growing on the rocks, and these guys come along and scrape it off. This is the immature form of a mayfly. The predators are things like stoneflies and crawfish. So they go and they actually prey on all those other invertebrates. There's a whole bunch of information about how invertebrates deal with flowing streams. Many have this streamline shape to themselves so that the water actually flows up and over them, reducing the amount of drag that would pull them and cause them to be pulled downstream. And then many of them have a phenomenon called drift, where when they want to move downstream, they actually let go of the rock, rise up into the stream current, and float downstream. So there's tons of work on the ecology of these different invertebrates. And if you care about things like mayflies, dragonflies, damselflies, the really beautiful dragonflies that are all over our creeks, this is the way to enter that kind of part of the science. A couple other pieces to know about streams. Groundwater seeps up into the streams, as we said. A good number of fish depend on that groundwater. They actually use it as sites of reproduction. They're called redds. Trout use these groundwater seepage areas. That's where they lay their eggs, where the groundwater is seeping out. I'm not sure, and I'm not sure what the science is yet on why they use the groundwater seepage areas. It could be that it maintains a constant temperature of water, particularly in the winter, because it's coming out at about probably around 50 degrees Fahrenheit. It keeps silt from forming on the gelatin-like egg so that the silt would prevent oxygen transfer into and out of the egg, and that stops that. It could be other reasons, nutrients or something that come into the eggs. I don't know the reasons, but a number of different fish species do rely on that groundwater seepage. Okay, and that brings us to this last part. So now you've gotten an overview of all the processes that drive ecology of streams. These are what are called the benefits that humans derive from having a healthy, functioning stream system. There are basically 9 ecosystem services of healthy streams, or benefits. The definition of an ecosystem service is the combined biological and physical characteristics of the wetland habitat, which result in processes that provide a large number of important benefits or services to human society. Personally, I value nature for itself. I love seeing it. It helps me spiritually. It makes me feel good I love the beauty of it. But in many places, people think that's not enough. And to them, then it might be worth developing, getting rid of a stream or polluting it. One of the ways we have started to change people's attitudes about that is to show them that they are benefiting from services that are provided by a healthy stream. In other words, they are saving money that would otherwise have to be spent. It's good to have in your mind what the ecosystem services are so you understand how critical it is that we maintain healthy stream systems. So I've kind of listed them. There are 9 I have here. I actually have like 11 and details on all of them, but we'll just give 9 basic ones here. And I think of them in terms of the above ground foliage of stream side vegetation, and then the below ground roots and ecosystems below ground and what they do for us. So we'll start with the above ground vegetation. So when the water levels rise and flood the banks and go over the shoreline and the stream sides, the leaves and stems intercept the water, they slow it down, and they cause materials to deposit out. In this schematic, I'm showing sediment depositing out and cleaner water passing through. It can be sediment, but it can also be big coarse material like these logs and branches and all that would clog up a bridge and cause rivers to flood over a road. When there's vegetation next to a stream, they also intercept things that are running off the landscape, and they're very important for capturing sediment coming off of, say, farm fields and trapping it before it ends up in the stream. When the vegetation intercepts the water, it also slows down the velocities. This is a graph, and there's not a ton of data on this, but it's fascinating. And on the horizontal axis is how fast the water is flowing. On the vertical axis is the height above the bottom, and what you see is the plant canopy. This is now a canopy of plants, and it's flooding, and the velocities when the water is flowing through the canopy are way lower. So they slow the velocity down, okay? That's important because then water is not racing at high speed down the streams. It slows down. The plants also even slow like velocity of boat wake. So like if you have a jet ski go by along a lake shore and if there's plants growing in the water, it could be cattails or water lilies, what you'll notice is far away from the shore where the wake first hits them, they move very rapidly back and forth as the waves hit them. But as you watch the wave come closer and closer to the shore, the plants have captured that wave energy and slowed it down through their own mechanical energy of waving their stems. So they reduce the amount of wave energy hitting the shore, and that reduces erosion. They absorb a lot of those, so those vegetated areas capture and hold a lot of that water, okay? That reduces flooding further downstream. And so this is a schematic showing a hydrograph. The green line is when you have a nice healthy vegetated shoreline and the water doesn't get as high as when you don't have a vegetated shoreline. You get a much bigger, faster peak. This is an actual real set of data in a project where they modeled how deep the water would be and how fast it would rise with and without having a healthy vegetated zone right next to the streams, and it rose much higher and much faster. A whole nother benefit we get is that in the headwaters of the stream, the canopy shades and cools the water. As the example on the bottom is a second order stream, 1 to 2 meters wide, 5 to 15 centimeters deep with a velocity of 5 to 10 centimeters per second. The daily maximum temperatures increased by 4 degrees over a 600 meter length when there was no shade. So in some cases, that's so warm that then things like trout who prefer cold water, they cannot exist there. And remember, our first and second streams are the headwaters. They accounted for 75% of the total stream channel network. You want them to be shaded and cooled so that they keep the entire stream river system much cooler. When the flooding occurs, we get another benefit. That water now allows fish to access a new habitat up in those floodplains. It brings in nutrients, it brings in sediment, seeds float up there, and the fish can go there, and they can actually, that's where they lay a lot of their eggs. And so that's our sixth benefit. The above ground leaves and stems and trunks provide refugia for juvenile fish. That means they're protected from predation. There's habitat there, there's lots of insects they can eat, and that is then effectively the nursery area for many of the fish we're interested in commercially even. They also provide habitat and food for some very cool animals. This is the star-nosed mole. I hope you'll hear about it when they talk about the mammalogy with you all. It occurs here. It actually occurs next to streams, and they form these little dark mounds. They use that very unusual structure on the front of their face. It can detect like electrical signals. So they actually swim around and can detect fish or earthworms like on the edge of a stream. They're very cool. That's all the above ground benefits. Now below ground. So alongside streams, you have a soil that's very brown, full of organic matter because it decomposes slowly when it's low oxygen. There are roots, microbes, animals. It's a whole ecosystem in itself. There's the root system adjacent to a stream of a tree that's been knocked over. The roots are really critical to help reduce erosion along streams. So as we worry about water quality and sediment moving in streams, we want to have roots that'll hold the sediment in place. Groundwater, as we said, flows from the upland areas through this wet area where the roots are and into the stream. As it passes through, there are a number of processes that help to keep it clean. Sometimes a contaminant can be absorbed onto the soil particles, like organic matter will bond with phosphorus or lead and help filter it out. The roots of the plants will take up excess nutrients and can actually keep excess nutrients from moving into the stream. And there are microbial transformations. A very important one is that nitrate, of which there is a lot in our landscape now due to manure, septic systems, and fertilizer, That nitrate in the fertilizers is can be at high concentrations very bad for human beings. It causes blue baby syndrome, which means they have a hard time getting oxygen. Turns out, as the groundwater passes through this wet organic zone next to the stream, bacteria under low oxygen will denitrify. That means they take the nitrate, use it in their metabolic cycles, and turn it into nitrogen gas and put it into the atmosphere. And so that nitrate doesn't make it into the stream. That's the end of the first whole half of this presentation. That was the ecology, the factors that drive the ecology of the streams, the hydrology, the geomorphology, groundwater and surface water, and the importance of understanding watersheds. The next half of this, the last part of all this, we'll look at how, what are the problems that are facing our streams and what are some of the solutions to those problems. Thanks.